Tony the Triangle Teletubby talking to you about congruence transformations. You ever see Transformers? Shot that in New York City. Big Apple, big dreams. Here we go.
First thing we do is review a transformation. That's a change in the position of a geometric figure. So in this chapter, we're going to talk about three different types of transformations: reflections, translations, and rotations. In this particular instance down here, we have our initial figure, triangle ABC, that we call our pre-image. We're going to talk about that more in a second. And it undergoes some type of transformation in order to get our resulting figure, which we call our image, triangle A prime, B prime, C prime. In this case, it was a translation, a slide. Over here, we have our initial figure, triangle XYZ, which we call our pre-image. It undergoes some type of transformation to end up with our resulting figure, which we call our image, triangle X prime, Y prime, Z prime. In this case, our transformation was a rotation. Now again, we just said the pre-image is your original figure, it's your starting figure, whereas the image is your resulting figure. It's what you get after you take your initial pre-image and perform some type of transformation to it. Now, a reflection or a flip is an isometry in which a figure and its image have opposite orientations. So here you can see we have our original figure, our pre-image, triangle A, B, C, and then our image, triangle A prime, B prime, C prime, after our pre-image was reflected over the x-axis, or sometimes they say reflected in the x-axis. And that just means that each point is flipped over the x-axis, meaning that each point is the same distance from the x-axis that it is on the opposite side. So point C is 2 units away from the x-axis. That means C prime is also 2 units away from the x-axis, just on the opposite side of the x-axis. Point B is 4 units away from the x-axis. Therefore, B prime is 4 units away from the x-axis on the other side. A, 1 unit away from the x-axis. A prime, 1 unit away from the x-axis on the opposite side. That's a reflection. Now, a translation or a slide is a function that maps each point to its image along a vector. So a translation, as you can see, is just a slide. You're going to take each point and slide it along a given vector. So here, our vector x is telling you that we're going to take each point in this triangle here, RST, and we're going to slide it along this vector, the same distance and in the same direction. So all you have to do then is apply this given vector to each point over here. So if I take this vector and attach it to point R, I can see that I'm going to take point R and slide it the same distance and in the same direction. So make sure these are the exact same distance and pointing the exact same direction, and we can put our R prime here. That is the image of point R after it's been translated along vector X. Let's do the same thing with point S. I'm going to apply vector X to point S, and I see I'm going to slide point S along the given vector and put its image right here at the end of the vector. This is S prime, the image of point S after it's been translated along vector X. Same thing with point T. I'm going to attach our vector X to point T and slide point T along vector X to where I get my image. Again, T prime is the image of point T after it's been translated along vector X. There is the image of triangle RST after it's been translated along vector X. Now, a rotation is a function that maps a point to its image through an angle x degrees, such that if the point is the center of rotation, then the image and the pre-image are the same point. If the point is not the center of rotation, then the image and the pre-image are the same distance from the center of rotation, and the measure of the angle of rotation is x degrees. So, this looks super complicated, but it's not. It's just saying that you have a point and you have its image. Your point is going to be rotated about a center of rotation x degrees. And once you do that, you will get the image of that point. Now there's two scenarios here. If the point is the center of rotation, so P at 0, 0 is our center of rotation, then the image and the pre-image are the same point. So no matter how many degrees you rotate P around the center of rotation, 0, 0, it will still end up being at 0, 0 because the point is the same as the center of rotation. As for part B, we have a point that is not the center of rotation. And when you have a point that's not the center of rotation, you are going to get another image point somewhere else after you rotate that pre-image point a specified number of degrees about the center of rotation. So what we're going to do here is we're going to rotate point P 180 degrees about our center of rotation, the origin, and we end up with our image point P prime at -6, -5. That is how you rotate when your point is not at the center of rotation. Please note that rotations are counterclockwise unless otherwise specified. This is very important because most of the time you will be asked to rotate either a point or a figure, and it will not tell you whether to rotate clockwise or counterclockwise. You just need to know that if it doesn't say, it's telling you to rotate it counterclockwise. Now, a congruence transformation, or isometry, is a transformation in which the pre-image and the image are congruent. And there's three types of isometries: reflections, translations, and rotations, what we just talked about. So all a congruence transformation is, or isometry is it's a transformation in which you take the pre-image, transform it using a reflection, translation, or rotation, or maybe a combination of the three, and you end up with your image. And your image is congruent to your pre-image. They're still congruent to one another, even after the transformation. So here you can see after a reflection in this line, the pre-image, triangle ABC, is still congruent to its image, triangle A prime, B prime, C prime. Same thing over here, triangle ABC, our pre-image, is still congruent to its image, triangle A prime, B prime, C prime, after a translation down and to the right. And you can see this five-sided figure right here, our pre-image, pentagon A, B, C, D, E, is still congruent to its image, pentagon A prime, B prime, C prime, D prime, E prime, after a rotation 180 degrees about the origin. That's why they're called congruence transformations.
Hey, where can I get an example time around here? How about now?
Now, example 1, to state whether the transformation appears to be a congruence transformation, or isometry. If it is, name the transformation. So, our pre-image is this darker blue quadrilateral right here, and our image is the lighter blue quadrilateral right here. So we're starting here and ending up here. So first, do these two quadrilaterals appear to be congruent? Yeah, it looks as though their corresponding sides and corresponding angles all appear to be congruent. So we can say, yes, these two figures are congruent, meaning that it would be a congruence transformation. Now the question is, how do you get from here to here? Well, couldn't I just take this rectangle and slide it right here? Yeah, so that would be a translation to get from your pre-image to image. So that's one way you could do it. Or technically you could also reflect it across a given vertical line right here and then slide it down. So it would be a glide reflection. Remember, a glide reflection is just where you reflect and then translate, or translate and then reflect. So, two answers for this. First, yes, it is a congruence transformation, and then the transformation could be a translation, a slide, or a glide reflection where we reflect and then translate. Part B, we have our pre-image and image here. So we're starting with this quadrilateral, this darker blue quadrilateral, that's our pre-image, and we're ending up at this lighter blue quadrilateral, this image. So first, do these two figures, these two quadrilaterals, appear to be congruent? Well, it looks as though their corresponding sides are not congruent, right? These sides here are smaller than the sides over here. The angles appear to be congruent, the corresponding angles appear to be congruent, but the corresponding sides don't look to be congruent. These sides in the image appear to be smaller than the sides of the pre-image. So we can say that these two figures are not congruent. So we don't have to name anything else. We just say that these two figures are not congruent. Done.
Hey, I got a pizza on the way. You try.
Okay, doing the same thing. So here, we're starting with the darker blue circle as our pre-image, and we're ending up over here with the lighter blue circle as our image. So first, do these two circles appear to be congruent? No, this lighter blue circle is clearly smaller than the darker blue circle. So these two figures are not congruent. So you just say, these two figures are not congruent, and you're done. Here, do these two figures appear to be congruent? So we're starting at our dark blue pre-image, this right triangle right here, and we're ending up at this light blue image over here, this right triangle. So first, do the corresponding sides and corresponding angles appear to be congruent? Yeah, they do. So these two figures appear to be congruent. Therefore, it would be a congruence transformation. Now the question is, how do you get from your pre-image to your image? Well, what I could do is I could actually reflect this blue pre-image over a vertical line. So if I were to flip that over a vertical line, and then I would have to slide it up a little bit. So what do you call it when you reflect and then translate, or translate and reflect? That's a glide reflection. So this is a congruence transformation, and it would technically require a glide reflection, a reflection and then a translation. Example 2 says state whether the transformation appears to be a congruence transformation or isometry. If it is, name the transformation. So this time, the only difference is that we're on a coordinate plane. So we have two quadrilaterals here, our blue pre-image and our red image. So first, do the corresponding sides and corresponding angles appear to be congruent in each of these figures? Yes, they do. Therefore, these two figures are congruent. So it would be a congruence transformation. So now the question would be, how do you get from your blue pre-image to your red image? Well, there's actually a few different ways. Since nothing is labeled, we don't have an A and an A prime or a B and a B prime. So technically, there's three different ways you could go from the blue pre-image to the red image. First would be a translation. If I were to just slide this blue pre-image over, I think 12 units, it would get me to this red image. So a translation to the right 12 units would be one of the transformations to get from your image to your pre-image. Another one would be a reflection over the line, x equals 0, or the y-axis. So if I were to reflect my blue pre-image over the y-axis, I would get my red image. Lastly, if I were to rotate this blue pre-image 180 degrees about the origin, I would actually end up with this red image. So again, it is a congruence transformation because the two figures are congruent, and there's three different ways to do it. A translation to the right, a reflection in the line x equals 0 or the y-axis, and then a rotation 180 degrees about the origin. All of those would get you from the blue pre-image to the red image. Part B, doing the same thing. So we have our blue pre-image and our red image. So first, do these two figures appear to be congruent? Do their corresponding sides and corresponding angles appear to be congruent? Yes, they do. Therefore, we could say that this is a congruence transformation. The only question is, what type of transformation? There's actually two different ways you could get from this blue pre-image to the red image. The first would be to reflect this blue pre-image over the line y equals 0, or the x-axis. If I were to reflect this image over or in the x-axis, or the line y equals 0, I end up getting this red image down here. You could also rotate this given pre-image about the point 6, 0, this point where they touch right here. If I were to rotate this pre-image 180 degrees about the point 6, 0, I would also end up with this image. So two ways to get from the pre-image to the image. That would be a reflection in the line y equals 0, or a rotation of 180 degrees about the point 6, 0.
Hey, I gotta catch a taxi, you try.
Okay, doing the same thing. So first, does this appear to be a congruence transformation? Does the pre-image appear to be congruent to our image? Do the corresponding sides and angles of our pre-image look to be congruent to the corresponding sides and angles of our image? Yeah, they do. So this does appear to be a congruence transformation. The only question is, what type of transformation? Well, there's actually two ways you could get from this pre-image to our image. One would be a 180 degree rotation about the origin. If you were to rotate this blue pre-image 180 degrees about the origin right here, you would end up with this image. The other way you could do this is you could reflect this given pre-image in the line y equals 0, so in the x-axis, so this top part would flip down here, this bottom part would flip up here. You could then take that and reflect it over the line x equals 0. So it would be a composition of transformations where you would reflect twice over the x-axis and then over the y-axis, but that would also get you to this image. So again, yes, it is a congruence transformation. You could rotate it 180 degrees about the origin and go from your pre-image to your image, or you could reflect your pre-image in the x-axis and the y-axis and you would end up over here. Part B. First, is it a congruence transformation? Does our pre-image look to be congruent to our image? Do the corresponding sides and angles of our pre-image look to be congruent to the corresponding sides and angles of our image? Yes. So it is a congruence transformation. The only question is, what type of transformation? So I'm going from here to here. Now again, nothing is labeled. None of the vertices are labeled, so you can't see any A or A prime. So there's actually a few different ways you could go from here to here. One would be to just slide this given pre-image down. If I were to take the pre-image and slide it or translate it down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units, that would give me the image. So this could be a translation down 10 units. Another way you could get from your pre-image to your image would be to reflect it over the line y equals 0 or the x-axis. If I were to reflect the pre-image in the line y equals 0 or the x-axis, that would get me from the blue pre-image to the red image. The last way you could do this is to rotate the pre-image 180 degrees about the origin. If I were to rotate this pre-image 180 degrees about the origin, I would end up with this red image. So yes, it is a congruence transformation. You could translate it down 10 units, you could reflect it over the x-axis or the line y equals 0, or you could rotate it 180 degrees about the origin. Now, example 3 says graph each pair of triangles with the given vertices. Then verify that it is a congruence transformation and identify the transformation. So first part says graph each pair of triangles with the given vertices. So we have triangle RST and triangle VWX. So let's graph these. Point R is at 1, 1. We go over 1 on the x-axis, up 1 on the y-axis. There's point R. Point S is at 5, 1. We go over 5 on the x-axis, up 1 on the y-axis, put point S. Then point T is at 3, 4. We go over 3 on the x-axis, up 4 on the y-axis, put point T. There's triangle RST. Triangle VWX. We're going to graph point V. Point V is at 1, 9. We go over 1 on the x-axis, up 9 on the y-axis, put a point. Point W is at 5, 9. We go over 5 on the x-axis, up 9 on the y-axis, put point W. Point X is at 3, 6. We go over 3 on the x-axis, up 6 on the y-axis, put point X. There is triangle VWX. Next, it says to verify that it is a congruence transformation. So we can't just, like we were before, say, yeah, they look to be the same. Here, we can actually prove it because we're given points. So with those points, how do we show that these two triangles are congruent? Well, one way I know to show triangles are congruent would be the side, side, side congruence postulate. And the way I do that then is show that each of the 3 corresponding sides are congruent to one another. To do that, I need to find the measure of each side. So let's start with the corresponding sides, segment RS and segment VW. So let's find the measure of those segments. So the measure of segment RS, how do I find that? Well, since I'm given 2 points, I can use the distance formula. Remember, to use the distance formula, I pick one of my points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. I then plug each of those coordinates into their corresponding spot in the distance formula, and I simplify. What is 5 minus 1? That's going to be 4. What's 1 minus 1? That's 0. So 0 squared is 0, 4 squared is 16. What's the square root of 16? That's going to be 4. So the measure of segment RS is 4 units. And really, you could have just counted since it's a horizontal line. Anytime you have a horizontal line or a vertical line, you can just count 1, 2, 3, 4. Look at that. Now let's find the measure of segment VW. So again, we use the distance formula. Pick one of your points to be x sub 1, y sub 1. The other one to be x sub 2, y sub 2. We plug them into their corresponding spot in the distance formula, and we simplify. 5 minus 1 is going to give you 4. 9 minus 9 gives you 0. 4 squared is 16. 0 squared is 0. 16 plus 0, that's just 16. And the square root of 16 is 4. Again, it's a horizontal line. You could have just counted 1, 2, 3, 4. Since segment VW and segment RS have the same measure, we can say that they are congruent to one another. Now we move on to the next pair of corresponding sides, segment ST and segment VWX. So segment ST, how do I find the measure of segment ST? I use the distance formula. Here we can't count because it's a diagonal line. It's not vertical or horizontal. So what I'm going to do is I'm going to pick one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. I plug these coordinates into their corresponding spot in the distance formula, and I simplify. 3 minus 5 is going to give me negative 2. 4 minus 1 gives me 3. Negative 2 squared is 4. 3 squared is 9. 4 plus 9 is 13. Rad 13 does not simplify. That's a prime number. So we know that the measure of segment ST is rad 13 units. Let's make sure that segment WX, the measure of that is also rad 13 units. So we start off with the distance formula. We pick one of our points to be x sub 1, y sub 1, and the other one to be x sub 2, y sub 2. We then plug in those coordinates to the corresponding spot in the distance formula. Then we simplify. 3 minus 5 is going to give you negative 2. 6 minus 9 gives you negative 3. Negative 2 squared is 4. Negative 3 squared is 9. 4 plus 9 is 13. The square root of 13 can't simplify, so we know the measure of segment WX is also rad 13 units. Since both of these sides measure rad 13 units, they must be congruent to one another. So now let's move on to the last pair of corresponding sides, segment RT and segment VX. If those measures are equal to each other, then we know those segments are congruent, and these two triangles then would be congruent by the side-side-side congruence postulate, and it would be a congruence transformation. So let's find the measure of segment RT. So to find the measure of segment RT, we again need the distance formula. We choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. We plug each of these coordinates into their corresponding spot in the distance formula, and we simplify. 3 minus 1 is 2. 4 minus 1 gives you 3. 2 squared is 4. 3 squared is 9. 4 plus 9 is 13. And again, rad 13 cannot be simplified, so we know the measure of segment RT right here is rad 13 units. Let's check to make sure that the measure of segment VX is also rad 13 units. So we again choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. We plug in these points to their corresponding spot in the distance formula, and we simplify. 3 minus 1 is 2. 6 minus 9 gives you negative 3. We then square the 2, we get 4. We square the negative 3, we get 9. 4 plus 9 is again 13, and the square root of 13 we cannot simplify, so we leave that as rad 13 units. So the measure of segment RT is rad 13 units, and the measure of segment VX is also rad 13 units. Since their measures are equal, we can say that these two side lengths then must be congruent. Because they are congruent, that means all three pair of corresponding sides are congruent. So these two triangles then must be congruent by the side-side-side congruence postulate, meaning that this is a congruence transformation. If I were to go from triangle RST to triangle VWX, it would be a congruence transformation. And the question is, how would you get from this triangle to this triangle? Well, one way you could do it would be to reflect it over this given line right here. The line y is equal to 5. A reflection in the line y equals 5 would transform this triangle right here into this triangle up here.
Hey, greatest city in the world, New York City! Time for you to try.
Okay, doing the same thing. So first, I need to graph both of these triangles. So we have triangle ABC and triangle EFG. So triangle ABC, let's graph each of these vertices. Point A is at 1, 2. We go over 1 on the x-axis, up 2 on the y-axis, put point A. Point B is at 1, 6. We go over 1 on the x-axis, up 6 on the y-axis, put point B. Point C is at 4, 2. We go over 4 on the x-axis, up 2 on the y-axis, put point C. There is triangle ABC. That looks like a right triangle. Next, let's graph triangle EFG. So graph each of these vertices. Point E is at -1, -2. We go over -1 on the x-axis, down -2 on the y-axis, put point E. Point F is at -1, -6. We go over -1 on the x-axis, down -6 on the y-axis, put point F. And then point G is at -4, -2. We go over -4 on the x-axis, down -2 on the y-axis, put point G. There is our triangle. Oh, it's looking like these two might be congruent. So we need to next verify that it is a congruence transformation going from our blue pre-image to our red image. So how do we do that? Well, again, one way to prove that two triangles are congruent would be to show that each of the corresponding sides are congruent. Therefore, the two triangles would be congruent by the side-side-side congruence postulate. So let's try that. The first pair of corresponding sides would be segment AB and segment EF. If we find those measures and they're equal, we can move on to the next one. So what is the measure of segment AB? We need the distance formula. So using the distance formula, I pick one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. I then plug in their coordinates to their corresponding spot in the distance formula and simplify. 1 minus 1 gives you 0. 6 minus 2 gives you 4. 0 squared is 0. 4 squared is 16. 0 plus 16, that's just 16. And the square root of 16 is 4. Therefore, the measure of segment AB is 4 units. Again, it's a vertical line, so you could have just counted 1, 2, 3, 4. Next, let's find the measure of segment EF. So here it is. We pick one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in those coordinates to their corresponding spot in the distance formula over here. And then we can simplify. -1 minus -1 is the same thing as -1 plus +1, so those just cancel each other out. We get 0. -6 minus -2 is the same thing as -6 plus 2, so that's going to be -4. 0 squared is 0. -4 squared is 16. 0 plus 16, that's still 16. And the square root of 16 we know is 4. So the measure of segment EF is also 4 units. Again, it's a vertical line. You could have just counted 1, 2, 3, 4. Therefore, both of these have the same measure. Therefore, these two segments must be congruent. Now let's move on to the next pair of corresponding sides, segment BC and segment FG. So to find the measure of those segments, we again enlist the distance formula. This time we have diagonal lines, so we can't just count. So I choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. I plug in those coordinates to their corresponding spot over here in the distance formula, and I simplify. 4 minus 1 gives you 3. 6 minus 2 gives you 4. 3 squared is 9. 4 squared is 16. 9 plus 16 gives you 25. And the square root of 25 is 5. Therefore, the measure of segment BC is 5 units. Let's check to make sure the measure of FG is the same. So we choose one of these points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula, and we simplify. -4 minus minus -1, same thing as -4 plus +1, so that's just -3. And then -2 minus -6, same thing as -2 plus +6, so that's going to be +4. -3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 we know is 5. Therefore, the measure of segment BC and the measure of segment FG are both 5, so they would be congruent to one another. Last but not least, let's find the measure of the last pair of corresponding sides, segment AC and segment EG. So to find those measures, we use the distance formula. We choose one of the points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula, and we simplify. 4 minus 1 gives you 3, 2 minus 2 gives you 0. 3 squared is 9, 0 squared is 0. 9 plus 0 is 9, square root of 9 is 3. Therefore, the measure of segment AC is 3 units. Again, it's a horizontal line, could have just counted 1, 2, 3. Down here, we could just count 1, 2, 3 and be done with it, or I could show you the distance formula still works. We choose one of the points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2, plug in the coordinates to their corresponding spot over here, and simplify. -4 minus -1, same thing as -4 plus +1, so that's -3. -2 minus -2, the same thing as -2 plus +2, so that's just 0. -3 squared is 9, 0 squared is 0, 9 plus 0 is 9, square root of 9 we already know is 3. So therefore, the measure of segment EG is 3 units, the measure of segment AC is 3 units, therefore those two segments must be congruent. So these two triangles then would be congruent by the side-side-side congruence postulate. Notice that they are also right triangles, so you could have proven them congruent by the hypotenuse leg theorem if you wanted to. You would have just had to show that one of the legs was congruent to one of the legs, the hypotenuse is congruent to the hypotenuse, and you would have to show that this is a 90-degree angle. So show that these two segments right here are perpendicular, and these two segments right here are perpendicular by finding the slope of each of those. I thought that was a little more work, so we didn't do that. Since we have proven these two triangles are congruent, we know this must be a congruence transformation to go from this blue pre-image to our red image. What type of congruence transformation? Well, it looks like we could just rotate triangle ABC 180 degrees about the origin, and we would end up with triangle EFG down here. So a rotation of 180 degrees about the origin would get you from your pre-image to your image. Another way you could have done it also is to reflect over the x-axis and then reflect over the y-axis. That would have been 2 transformations, so I just wrote the 1 right here. So your answer, yes, it is a congruence transformation, and the transformation would be a rotation 180 degrees about the origin.